Okay, so maybe we can start. Everybody, welcome to the second seminar in this second series of Akademgorodok Forum. And it's my pleasure to introduce our today's speaker, Dan Segal. Dan Segal is a professor of mathematics at University of Oxford, and he is, of course, very well-known specialist in group theory. He wrote 5 monographs with some with co-authors. He is famous for excellent results about polycyclic groups, about growth in groups and profinite groups, and also about width, his famous results with Nikolov, and so on. And now he will speak about connections with logic. The title is Groups, Rings, and Logic. So to you, Dan, start.
Okay, thank you very much, Evgeny, and thank you. I feel very honored to be invited to contribute to the Kurovka meeting. So when I think of Kurovka, of course, I think of problems. So I thought I should probably start with some problems. But what I'm going to talk about, well, maybe first not about any specific problem, but about what might be a program. I don't know if it deserves to be a program, but it certainly goes back a long way, particularly to Maltsev, who was probably the first or one of the first to study how much algebra can one do using only the tools of logic, first order logic particularly. Because as you all know, of course, if you try to say interesting things about infinite structures using first order language, you can't say very much, because algebraists like to talk about subgroups, subrings, collections of subsets and things like that. And these are all things which are not easy to pin down using first order language. Okay, so the particular kinds of problems I was concerned with came up. Well, I was introduced to this by Andre Nies a few years ago, and he was interested in the question of which groups can be axiomatized, by which he means if you've got a group G and another group which satisfies the same first order properties as the group G, must the second group be isomorphic to the first group? Of course, because of the Löwenheim-Skolem theorem, you've got to add something about the size of the things you're talking about, because if a first order theory has an infinite model, it will have infinite models of different cardinalities, so you can't actually pin down something like a group just by its first order properties. But if you insist that we only consider groups which satisfy some extra control on the size, for example, being finitely generated, then it turns out you can say quite a lot, and there are some surprising positive results. And what Nies asked me specifically was, what can you do about profinite groups, which of course as abstract groups are not going to be finitely generated, but they are finite in another sense. They have a compact topology. So if you specify some first order conditions and then say, suppose you consider a profinite group which satisfies these conditions, how much can you say about it? Right, well, let's go on to the slides. Okay, so the vague question I've said, how much can you say? And which groups can be determined by their first order properties, and which groups can be a particular challenge is, can a group be specified by a single first order sentence? These are groups which are called finitely axiomatizable, which I'll call FA. And as I said, you have to consider them groups in a particular class of groups because of cardinality problems. So Andre Nies wrote several papers about these groups he called QFA, quasi-finitely axiomatizable, namely the groups which are determined up to isomorphism among finitely generated groups by a single first order sentence. And he produced several examples. And then Francis Auger and Gabriel Sabat actually produced a nice characterization of those finitely generated nilpotent groups, which are QFA, finitely axiomatizable among finitely generated groups. Not all of them, as we'll see in a minute, but quite a lot. Does this go like this? Yes. Okay. I'll come back to the nilpotent groups in a minute. And I'll now move on to profinite groups, which is not the only topic, but it's going to be kind of half of my subject. The problem in a profinite group is that it's actually quite difficult to define things inside it, because you can't really talk about the topology using group theory, using language of group theory. But there's a way of producing definable subsets, which is like this. Suppose you have something like a finite subset or a definable subset more generally, then the subgroup it generates is usually not definable. And if you're in a profinite group, the closed subgroup it generates is even less definable. You can't even define it algebraically. But if you take the set of products of some bounded number of elements from your set, then of course you can define it easily by a sentence. I call that x star n, the product of n elements of x. Okay. Now, there's a well-known lemma in profinite groups, which says that if you're in a profinite group G, and you have a finite set X, or more generally a compact set X, then the subgroup it generates is closed in the profinite group, if and only if it has finite width. In other words, every element of the subgroup is a product of boundedly many elements of the set X. So if you have a definable set and the subgroup it generates has finite width, then the subgroup is definable. And if the set you started with is closed in the profinite group, in the profinite topology, then the subgroup it generates is again closed, because it's just a product of finitely many compact sets. So this way you can find lots of definable closed subgroups, if you're lucky, if you have this finite width problem. Well, there's this nice result that I proved with Nikolai Nikolov, which says that in a finitely generated profinite group, the subgroup generated by mth powers for a fixed positive integer m is closed. But of course, what we proved is that the mth power word has finite width. Every product of mth powers is a product of boundedly many mth powers. It only depends on the number of generators of the group, actually, and on m. Okay, so the subgroup it generates is closed, and then because of the restricted Burnside problem, a closed normal subgroup such that the quotient group has finite exponent is actually going to be an open subgroup. And as I said, it's definable. So in particular, if you look at the quotient groups, G modulo G to the m for positive integers m, these are all going to be describable in first order language. Because if you're, well, first of all, you can identify the elements, as it were, the cosets of this subgroup of finite index. And then, of course, you can specify the multiplication table by some first order sentences in the language of groups. So in other words, the finite quotients of such a profinite group can all be described using first order group theory language. So what does that tell you? Well, this is the first time I think that the idea that this might be useful for sort of model theory questions was realized. This was by Alex Lubotsky and Moshe Yarden. So they proved that a finitely generated profinite group is determined up to isomorphism in the class of all profinite groups by its first order theory, the first order sentences it satisfies. And the proof is what I've just given you. You can describe each finite quotient using first order sentences. And of course, the group is the inverse limit of its finite quotients. So that determines it up to isomorphism. Of course, you need infinitely many sentences to describe such a group. You need to describe all its finite quotients. So a profinite group, even finitely generated, is usually not finitely axiomatizable. And there's a sort of obstruction which explains why this often can't happen. And this was done for abelian groups by Vanda Shmielev back in the 1950s. And then Auger and Sabat, in their paper, produced a general results about any group which has too much center. It looks a bit like an abelian group in the sense that some infinite cyclic part of the center is visible above the derived group. Specifically, the center times the derived group modulo the derived group is not periodic. Okay, you have a group like that. Then if phi is any first order sentence satisfied by the group G, then for almost all primes Q, the direct product of G with a cyclic group of order Q satisfies the same sentence. So actually the proof is very beautiful, but if I was giving a seminar with a blackboard, I might give you a hint of the proof, but I better not stop. Anyway, it's very nicely written up in the paper of Auger and Sabat. So anyway, this is an obstruction to finite axiomatizability. So any group which is not isomorphic to its direct product with CQ for infinitely many different primes Q can't be finitely axiomatizable if it satisfies this condition of having too much center. So for example, the property of being a pro-P group can't be determined among profinite groups by a single sentence. And groups like the infinite procyclic group, profinite completion of the integers, can't be finitely axiomatizable for the same reason. Okay, so where do we go from here? If we avoid this obstruction, oh yeah, being generated by D elements can't be described by a first order sentence either. Okay, however, if you stick to pro-P groups, if we assume that a group is a pro-P group, then of course that obstruction doesn't arise because, sorry, the obstruction does arise, but let's go back. Oh yeah, it doesn't arise because the group G cross CQ may satisfy the same sentences as G, but it's not a pro-P group if Q is a different prime. So you can get rid of that problem in that way. The other thing you can do is you can also control the number of generators, which is very important, because if you have a finitely generated pro-P group, it's a Frattini subgroup, has finite index, just at P to the D, where D is the number of generators. And this is a situation which can be expressed in first order language, because, well, maybe it's not obvious, but it's certainly true. One has to talk about the width of the derived word and the pth power word. But in pro-P groups, these do indeed have finite width. Okay, so you can specify that a pro-P group can be generated by D elements. And the pro-P groups which are particularly nice are the ones which are called p-adic analytic. So they're the ones which have finite rank in the sense of proof of rank. In other words, every closed subgroup can be generated topologically by at most R elements. These are the groups of finite rank. And when I first gave this talk, I mentioned this lemma that you can specify that the group has rank about R by a first order sentence, but I couldn't actually pin it down exactly. So there's a sentence rho R such that if the rank is less than at most R, then the group satisfies this sentence. And if the group satisfies this sentence, its rank is bounded above by a small function of R. But in fact, quite recently, Benjamin Klopsch and his student, Martina Conte, answered my question. And actually, they can produce a first order sentence which specifies the exact rank and also the dimension, which is something I haven't defined, which is a number which might be slightly smaller for a pro-P group of finite rank. So that's quite nice. And it gives one the hope that if we stick to p-adic analytic pro-P groups, maybe one can say quite a lot about them using first order language. And in a sense, that wouldn't be too surprising because these groups have got a finite dimension. So they're not actually finite as sets, but they have a lot of finiteness. They look like finite structures in a lot of ways. So the first result that Andre and I proved with Catherine Tent was finite axiomatizability for these pro-P groups of finite rank. So suppose G is a p-adic analytic pro-P group. Then G is finitely axiomatizable among pro-P groups. But you have to make a little extra condition. You have to assume either that the group has a finite pro-P presentation using actual finite group words, or you enlarge your first order language to allow symbols for p-adic powers in your group. What I mean by having a finite pro-P presentation using finite group words means that, well, it's what it says. A finitely presented pro-P group, the relators might in fact, they're elements of the free pro-P group, but they might not be finite group words, they might be infinite group words. Okay, so I'll explain why that has to be there in a minute. But before I do that, I'll mention the next theorem. We looked at the theorem of Auger and Segal that I mentioned. They characterized finitely generated nilpotent groups, which are finitely axiomatizable among finitely generated groups. And we produced an exact analog for finitely generated nilpotent profinite groups. You see, I've moved away from pro-P groups, but for a minute, you'll see that, in a minute, you'll see that I haven't gone very far from pro-P groups. Okay, so the result is this. A finitely generated nilpotent profinite group is finitely axiomatizable in the class of all profinite groups, if and only if one, it only involves finitely many primes. And two, the center modulo the drive group is finite. In other words, this obstruction, which would stop it being finitely axiomatizable, has been abolished. Okay, you need that. And we also have to assume these conditions, either the group is finitely presented among pro-P groups, but using a finite group words, that's what I call A, or we allow symbols for p-adic powers in the first order language. So that's quite a nice characterization, I think. It exactly parallels the result for finitely generated abstract groups. Oh, on the slide I explained the extra assumptions are necessary, these assumptions A and B, because of course there are uncountably many groups. Because, well, you can write down pro-P presentations using pro-P, using parametrized by p-adic integers, for example. But in the first order language of group theory, there are only countably many sentences. So you couldn't describe uncountably many non-isomorphic groups using countably many sentences. But if you allow yourself p-adic powers, then the problem goes away, and then you can do it. So that's the extra assumptions. Right. Let me just say a quick word how we do. There are two parts to the proof of this, to the positive part. We want to show that one of these groups is finitely axiomatizable among profinite groups. Sorry, among pro-P groups. I'll stop there. Yeah. No, sorry, this is the one. It's finitely axiomatizable among all profinite groups. Now, there are two parts to the proof. First of all, you've got to, well, first of all, you're only allowed finitely many primes because of a piece of model theory, which I might mention in a minute. Given finitely many primes, you might as well assume it's a pro-P group. Well, I'll assume that. It's a small argument. Once you know it's a pro-P group, you have to be able to specify what the prime P is using first order language. And that uses some group theory, using this fact that the group is nilpotent. You have to find the prime P. Once you've found the prime P, you've then got a group which is finitely generated nilpotent and a pro-P group. So it's a p-adic analytic pro-P group. And then you can quote the previous results. Then you know it's a pro-P group, then among pro-P groups, it's defined by a single sentence. And therefore, if you go back to the original problem, it's defined by a single sentence among profinite groups. So this comes up quite a lot, certainly in profinite group questions. One part of the problem is to specify the prime. Once you know the prime, you then work in pro-p groups. Okay, now, of course, nilpotent groups are not very exciting. I shouldn't say that in front of Evgeny, actually, but they have their own problems. But a lot of people are interested in things like semi-simple groups and more complicated things, where you don't have so much commutativity. But we can apply these, for example, to groups like SLD, because in a group like that, big reductive group, you've got a very large nilpotent subgroup. You've got the upper unitriangular matrices. That's a nice finitely generated nilpotent pro-p group. And provided you can show it's definable inside the group by some first order sentence, you can then use our previous theorem, that one, to say that the structure of that group is then definable, is then determined by a single first order sentence, okay, of this unitriangular subgroup. And once you know that, that tells you that the group is, it tells you what the prime p is. This is the interesting thing. Once you know what the prime p is, you've got this group. It's a pro-p group. It's a p-adic analytic pro-p group. Well, I'm telling a lie. If you take the first congruent subgroup, it's a pro-p group. So it's virtually a pro-p group, and it's p-adic analytic. So we can use the other theorem about p-adic analytic pro-p groups, and that pins this group down. Okay, so that was, as it were, the first part of our project, the profinite part. But once we looked at SLD-ZP, we thought, well, suppose we took other rings instead of ZP. What can we do? It might get more difficult. Certainly the group theory becomes much more complicated. For example, even if you take a nice ring like FPT, the power series in one variable over a finite field FP, you can look at SLD over that ring. It's kind of an analytic group, but group theoretically is very, very far from having finite rank. It has these huge elementary Boolean subgroups. So the kind of methods we were talking about don't really get to grips with it at all. However, the ring might be easier to deal with than the group, because the language of rings, of course, is much stronger than the language of groups. As a simple example, you can think of the additive group of the p-adic integers is certainly not finitely axiomatizable among profinite groups because of that general obstruction I mentioned earlier. But as a profinite ring, it's very easy to specify the ring of p-adic integers, because basically you can say, you can identify the prime p by saying that everything not divisible by p is a unit. That's the kind of thing you can do. So, okay, before I do that, let me just go back to why we're only allowed finitely many primes when talking about, for example, nilpotent groups, or indeed groups like SLD of Z pi. So that would be a nice profinite group where you have a profinite ring in there which involves infinitely many primes. Well, there's a model theoretic result called the Pfefferman-Vort theorem, which logicians will know, which says that if you have an infinite Cartesian product of structures, you can specify the first order properties of that infinite product entirely in terms of first order properties of the factors and the Boolean algebra of subsets of the index set. And in particular, if you have an infinite set of primes, then anything which is true for something like Z pi, for example, a first order sentence, will still be true if you replace pi by a slightly perturbed set of primes. You can take one prime out and replace it by another. Of course, you can't say which one, but this general model theory result will say that you can't really talk about infinite products like that very precisely. That's a bit vague, but that's why you need to consider finitely many primes. Okay, let's move on. So as I said, using group theoretic methods, you can get so far with, for example, profinite groups, but you can't get very much further. But if you look at this group SLDZP, as I said, you've got this ring there, and obviously you can express group theoretic properties of the group by ring theoretic properties of the ring. To multiply two group elements, you simply form matrix products, which are made using sums and products of ring elements. Okay, if you can express all the group theoretic properties of the group as ring theoretic properties of the ring, then you could, for example, deduce that the group can be axiomatized in group language once you know that the ring can be axiomatized in ring language. As I said, that's quite easy for the p-adic integers. So there's a machine for doing this invented by model theorists called bi-interpretation. So you have a ring and a group, and there's a way of describing group in terms of the ring, and you have to describe the ring in terms of the group as well. And then you can read off first order properties of the group from first order properties of the ring, and vice versa. So I will give a sort of slightly simplified definition of this. You have a group gamma and a ring R. And of course, logicians will say these could be just any two structures with their own languages, but we'll stick to groups and rings. So first of all, gamma is interpretable in R, which means you have some finite product of copies of R, and you can define the group as a subset of that. You can define both as a set and its operations can be defined using ring theoretic language. And when I say sits definably, model theorists like to allow not just as a subset, but also as a, what they call, they talk about imaginaries, which sounds very mysterious, but basically you're allowed a definable equivalence relation on this set. And then the group is allowed to be a definable set of equivalence classes. But for our purposes, we'll just say it's a subset, a definable subset. Then the same thing the other way around. You can define a copy of the ring inside some product of copies of the group. And the ring operations must also be defined using just the group theoretic language of the group. So these are the sort of two obvious things. You can interpret each in the other. And the third one is more subtle. You start with the group. You're embedding it into some copies of the ring. You then embed some copies of the ring into even more copies of the group. And so you end up with a copy of the group sitting inside some large product of copies of itself. Okay, so you've got a map from the group gamma into gamma to the Mn. And this map is certainly an isomorphism just from the way it was set up. But what you require is that this mapping should be definable using just the language of the group gamma. And that's usually the most difficult thing to prove when you're trying to establish this kind of situation. Okay. Oh, it's supposed to be symmetric as well. There's a condition called 3 bis, which swaps gamma and R. But for the situations we're dealing with, this is going to be obvious, so I won't talk about it anymore. Okay, anyway, if you've got this situation, then any first order property of gamma can be expressed as a first order property of R. And any first order property of R can be expressed as a first order property of gamma. It's kind of obvious routine, really. If you want to say that, you know, X times Y equals Z in the group gamma, you're simply saying that some matrix, suppose it's a group of matrices, some matrix times another matrix equals a third matrix, which you can express using ring theoretic language. Okay, So the first order properties of gamma correspond to first order properties of R. In particular, if R is finitely axiomatizable using ring language in a certain class of rings, then gamma is finitely axiomatizable using group language in a corresponding class of groups. And of course, you have to be clear what the restrictions on the group mean for the ring and vice versa, so we know which classes of groups and rings we're talking about. But we'll see what this is in practice. And as it could be finitely axiomatizable, or it could be axiomatizable in the wider sense, namely determined by its first order theory. The same thing works. And we'll see examples of both. Okay, let me just illustrate this with the group I started with, D by D matrices of determinant 1. Okay, the group gamma can be identified with D by D matrices of determinant 1. So gamma is a subset of D squared copies of the ring, D by D matrices, and it's definable by this condition determinant equals 1. That's a polynomial condition. And the group operation is definable by matrix multiplication. Okay, so that's kind of the obvious situation where this thing first came up, I imagine. How do we define the group the ring in terms of the group? Well, this is a well-known thing. And this actually, I think, was used by Maltsev, this very explicit thing, certainly for upper triangular groups. You consider the matrices of the form with just one non-zero entry in the 1, 2 place, the root subgroup U1, 2. So you've got the identity matrix plus, well, an elementary matrix. Okay, so if you just read off the entry in the 1, 2 place, you get a ring element, and every ring element occurs. And if you multiply two elements like that, two matrices like that, you're adding the ring elements. So that's easy. If you want to multiply the ring elements, you have to be a bit more clever. You have to use the commutator map. This is exactly what Maltsev did, in fact. So you take the root subgroup U1, 2 and the root subgroup U2, 3, and you consider the commutator map between them. And what you get is a matrix with one entry in the 1, 3 place, which is the product of the two entries you had in the other two places. Okay, so you're saying, you might say, well, the trouble is these are the wrong subsets of the group because the ring is identified with U1, 2. Okay, well, you then conjugate these back into U1, 2. And so you get a map from U1, 2 cross U1, 2 into U1, 2. And so you can define the ring multiplication using just group multiplication, or commutators and conjugates. Okay, so these two are fairly straightforward. And now the subtle part, you actually have to do a bit of work. You have to show that if you take, you've got a map from gamma to R to the D squared, and R is embedded in U1, 2, so you've got gamma maps into D by D matrices, and each entry of the matrix is again an element of gamma, a root element. And so what we have to show is that this mapping from gamma into these D squared tuples of elements of gamma can be defined using group language only. You have to show in particular, so for each pair ij and for each element g in the matrix group, the element of U1, 2 that represents the entry the matrix entry Gij can be defined group theoretically inside gamma. So that's requires a bit more thought. But that's kind of the main content of the result. Okay, so once you can do that, you can deduce that that gamma is bi-interpretable with R. That's exactly what these things say. Okay, so I worked on this with country intent, and we thought, well, if we can do it for SLDZP, how generally can we do it? And this is what we came up with. Let G be an adjoint simple Chevalley de Mazur group scheme of rank at least 2. And let R be a commutative integral domain. Then the group GR is bi-interpretable with the ring R. And I put a bracket almost always because we didn't quite prove all cases. I will explain the gap in a minute, but it's probably true in all cases. So what's a Chevalley de Mazur group scheme? Well, if you've got an integral domain, you can just think of it as the R rational points of an ordinary Chevalley group defined over the field of fractions of R. But we do actually use the group scheme idea in the proof. And what about almost always? So to be honest, we can't quite prove it when G is of type E or F, E6, E7, E8, or F4, and R has no non-trivial units. So this is a rather nasty ring. It has characteristic 2. So it could be something like F2 of T. But it's probably true, but the proof gets a bit too hairy. We could calculate these cases. But if the ring doesn't have characteristic 2, for example, this is completely true in full generality. Okay, so before I go on about the proof, I should say a bit about other results that people have got. I think the first result in this direction recently, anyway, was obtained by Avni, Lubotsky, and Mary, again about 3 years ago. They didn't do the bi-interpretation, but they proved axiomatizability, not finite axiomatizability, but axiomatizability. In other words, first order properties determine the group for a lot of arithmetic groups. So their groups are more general than mine because they don't have to be Chevalley groups. They could be generally, I think, semi-simple algebraic groups defined over the rationals, not necessarily split, but their methods only work for the ring Z. So our results are more general in terms of the ring, but they do apply only to split groups. Though some of the methods may well generalize, and this is part of a project which might be interesting to people. There's more recent work by Avni and Mary, which is actually quite exciting. Again, they only talk about arithmetic groups, but they proved a remarkable result, I think, to me, which is that, I haven't written it down, but I'll tell you because I think it's quite important. They prove for a lot of arithmetic groups that they are bi-interpretable with the ring of integers. Not all, but a lot. And for some very special ones, like PSL2, PSLN, N at least 3, they prove something even more remarkable. They prove that this bi-interpretation can be done in a uniform way where you allow the rank to go to infinity. Because everything we do depends very much about having n by n matrices for a fixed n. Now they use some clever trickery with Gödel numbering and so on to encode the rank, for example, of SLD, the number D, they managed to encode that as well. And so they prove, for example, that there is a single first order sentence which says of a finitely generated group gamma that gamma is isomorphic to PSL n of R for some integer n, at least 3, and some ring of algebraic integers R. So I think that uses quite sophisticated methods, and I think that there's probably a lot of future in that, but it's slightly off my subject, but I wanted to mention it. So Avni and Mary. Okay, so let me go on and say a little bit about how one proves this bi-interpretability thing. Actually, in fact, I won't. I'll come back to that. First, I'd like to say a little bit about conclusions we can draw from this. If we could go back to first order properties. So I'll go back to okay, so we've got the group gamma, which is G of R, and we've got this integral domain R. What can we deduce about axiomatizability? Well, every finitely generated ring, commutative ring, is finitely axiomatizable in the class of all finitely generated rings. That was proved in a paper by Aschenbrenner, Hilif, Nazasieno, and Scanlon a few years ago. So from this, we can immediately deduce that corresponding result for Chevalley groups over these rings. I'll come to the statement in a minute. Secondly, what was interesting to us when we were doing the pro-p case, suppose you have a ring like FQ double square brackets T. So FQ is a finite field and T is a finite set of variables, and you form power series. This is a pro-p ring, it's a profinite ring. Or you could consider a ring which looks like the p-adic integers, or a finite unramified extension of the p-adic integers, OQ, and again form power series. So these rings are finitely axiomatizable in the class of all profinite rings. So we proved that in our paper. It's not very difficult, however, because the Ayers-Cohen structure theorem for complete local rings says if you assume a complete local ring is regular and unramified and has finite residue fields, then it's exactly one of these rings. And they're determined by two parameters, namely Q and, well, three really. The characteristic, the residue field Q, and the number of variables. So these rings can be finitely axiomatized among profinite rings. And so you get something about profinite groups, which are Chevalley groups over these rings. And then we asked Matthias Aschenbrenner, are locally compact fields finitely axiomatizable? Local fields. And the answer is yes. And again, that using known theory of these fields, that's fairly straightforward. So again, so the groups which are locally compact, which are Chevalley groups over these fields, will be finitely axiomatizable. So here's the result we can deduce from all that. So G is a simple Chevalley group scheme. R is an integral domain, and gamma is G of R. Okay. Suppose gamma is finitely generated as a group. That's all we have to assume, right? Well, then you can deduce that the ring is finitely generated. And then it follows that the ring is finitely axiomatizable among finitely generated rings. And it follows from the bi-interpretability that the group is finitely axiomatizable among finitely generated groups. So that's the most general results about axiomatizability, finite axiomatizability of finitely generated groups, I think. It's the most general result we have anyway. Going back to profinite groups, these groups are virtually pro-p. You have one of these nice rings, these nice pro-p rings. You take a Chevalley group, a simple Chevalley group over one of these rings. This will be a profinite group. It will be virtually pro-p, they're not pro-p. And this will be finitely axiomatizable among profinite groups. And then finally, these groups are popular locally compact groups. So if R is a local field, then this group gamma is a locally compact group, and it's finitely axiomatizable among locally compact groups. And you can read the details in these two papers. One has just appeared in PLMS, and the other one is on the archive at the moment. Okay, so that was my sort of concluding result. But now I'd like to go back and talk for a few minutes about the proof, because once we worked out how to do it, it's not all that difficult, though there are technical complications. So the first step is we want to define the ring inside the group, right? So we've got a Chevalley group, think of, you could think, and it may not be adjoint, but I'll need it to be adjoint for the final bit of the proof. So suppose you have the Chevalley group G and a root subgroup U alpha. Alpha is one of the roots. And then take a non-identity element in U alpha of R, then it's actually the center of its centralizer in the group. GR is the group gamma. So this subgroup U alpha of R, the whole root subgroup, is definable, obviously, as a double centralizer. Okay, I said usually because when we were working on this, we asked lots of experts, and they said, "Is this true?" Because we thought it's probably true. It's kind of very easy to see for SLN. And everyone said, "Yes, of course it's true. Of course it's true." But then we actually found it's not always true. There are cases where it isn't true, even for Z. If G is a symplectic group and R is a ring of integers, for example, which has at most 2 units, then this is not quite true. The subgroup U alpha of R is still definable, but it is slightly larger than that. Larger or smaller? Larger, certainly contained in there. Okay, so once you've got this, that shows that U alpha of R is definable in G of R. So we can use it to interpret the ring inside the group. Now, as we did with SLD, you have the Chevalley commutator relations in your Chevalley group. And then you can get a commutator map between 2 root subgroups mapping to a 3rd root subgroup. And then you have to play around a little bit, moving the subgroups around and so on. And end up defining the ring multiplication on the ring using commutation between 2 root subgroups. And possibly conjugation, possibly have to do some other trickery as well, depending on the root system. It's a bit technical, but it all works out. So this does the first part of the bi-interpretation, interpreting the ring in the group. Okay, oh, so the second part, I should say. The first part was to interpret the group inside the ring. Well, that's given. The group is essentially defined as a group of matrices over the ring, satisfying certain polynomial equations. That's not how it's defined as a Chevalley group, but it is how it's defined as a Chevalley group scheme, actually. I mean, a Chevalley group is defined by its generators using root subgroups. But if you take the group scheme, it's by definition, the scheme consists of, will be matrices which satisfy certain polynomial equations. And again, the group operation is just matrix multiplication, so that's easy. Now, the difficult part is point 3. We've got this map from GR, from GR to D by D matrices over R, and then back into D by D matrices with elements in the group. And so you've got a map from the group to matrices over itself, and you've got to show that this map can be defined group theoretically. Okay, so how do we do this? Well, there's one case where it's quite easy. We're coming back to finite width. So remember, each ring element can be identified with a group element, namely as a root element X alpha of R, where alpha was our chosen root. Okay, so the map goes from gamma, the group, to SLD of R, namely G goes to its ij entry is Gij, then the little dash means the element of, sorry, if G goes to Gij, that maps into SLDR. And if you identify each element R with R dashed, namely the root element X alpha of R, you get something in gamma again, U in fact, the root subgroup. So if you combine these two maps, you get this map from gamma into D by D matrices with entries in the subgroup U, so which is sitting inside D squared copies of gamma. So we want to show that this map is definable in group theoretic language, okay, which means you have to define each component. For an element G in gamma, how do you define Gij dashed inside U? Okay. Well, suppose G itself was a root element, okay? So you've got a root beta. Then the group element X beta of R can be defined in terms of R by certain polynomials. People who remember their Chevalley groups will know that it's usually just either R itself or possibly a little quadratic thing in R. In the case of SLD, you know, U12 of R was just had R, the entry R itself. So these polynomials are very often just the identity or there might be some little quadratic things. Anyway, they're specified and they're known. So if you think of Gij as an element of the ring, Gij dashed is just some polynomial in Gij. Well, not some polynomial, but the image of some polynomial inside U. Okay. Of course, we want to get it into U. We've got it in U alpha, right? We've got it in U beta, but you can either conjugate it into, you can either conjugate U beta into U alpha, or you can conjugate it and then commutate with something from another root, depending on the root system. Anyway, the upshot is that if you're given an elementary root element, x beta of R, you apply theta to it, you get something which you can define group theoretically. So it's probably a bit difficult to take in, but if you see it written down, it's not too difficult. Okay, so why is that useful? Well, because if you have a product of finitely many root elements, some given number of root elements, you can define the map theta on that product because you can define it on each term, right? So if we consider the set E capital N of R, which is the set of all products of n elementary root elements, then you can define theta on any such product because you can define it on each individual root element. Okay, so the restriction of theta to this set En of R is definable. Okay, now if you're very lucky, there will be some n such that everything in the group is actually a product of n elementary root elements. In that case, the group GR has finite elementary width. So what I've said so far actually explains why this is true. If the group GR has finite elementary width, then GR is bi-interpretable with R. That sort of deals with that case. There are lots of cases where it's true. If R is a field, this is basically the Brouillard decomposition, gives you this elementary width property. If R is a local ring and G is simply connected, it's a theorem by Abe. Quite a long time ago, he wrote a paper about Chevalley groups over local rings. And you might say, I assumed G was adjoint, but I didn't actually. We need G adjoint for the next case. But if G is simply connected, we can apply Abe's theorem when the ring is a local ring, and we're done. If R is a ring of S integers in a number field and G is simply connected again, Tavgen proved that G of R has finite elementary width. That's for the arithmetic groups. So in all of these cases, our group will be bi-interpretable with the ring R. And these don't require the group to be adjoint. Okay, what about the general case? I won't give you the full details, but I'll say if G is adjoint, the centralizers of all the elementary root elements actually intersect in the identity because they generate the group. Okay, so you can specify an element. Right, so you can specify an element of the group by specifying how it conjugates every elementary root element. That determines it because it's specified, it's determined up to the center of the group. Okay, now theta is a group isomorphism from GR to its image in matrices over U, if you remember. So to determine G theta, it's enough to determine it on elements which are conjugates of root elements by arbitrary elements. If you want to know what little g theta, what theta does to little g, it's enough to know what theta does to this thing, x beta 1 conjugated by g. And now we're sort of getting close to the answer because we know what theta does to x beta 1. I've already said that. Okay. And now, when we discovered this result by Stepanov, we thought, aha, this is going to solve the problem. Stepanov showed that even if the group doesn't have finite elementary width, every conjugate of an elementary matrix, x beta 1, is actually a product of boundedly many elementary matrices. And if I had longer, I would explain the proof of this because it's very beautiful. It's a very beautiful use of the fact that you've got a group scheme and you use a generic element. That's what the heading of this little section. So it's on my slide, but I won't talk through it. Anyway, Stepanov observed that every conjugate of an elementary root element is in fact a product of boundedly many elementary root elements. So once you know that, you see, I've already pointed out that we know how to define the map theta on this set, E capital N of R. So that means we know how to define theta in particular on each of these elements, x beta 1 to the g. And once we know what theta does to each of these, we know what it does to g, because the action of g on these elements determines g, and also determines g theta, because theta is an isomorphism. Okay, so we argue as before, and this establishes the main theorem. In the case of an adjoint group, you see, that's where we needed the adjoint condition. Okay, I'll leave out the sketch proof of the lemma because my time is up. But if anybody would like to, I don't know if you've copied the notes, or I can send them to you. You see, it only takes about a page and a half. So let me just wind up with a couple of questions. Oh, the first thing I was going to say, there are some slightly more general results, but I won't spend time on them. Another result, which is, I think, quite interesting, is that I didn't talk much about the topology in the profinite groups case, but one has to actually keep track of the topology when you're defining. If you've got a group and a ring, and it's a profinite group, you need the ring to appear as a closed subset, so it's also a profinite ring, and vice versa and stuff. So you have to do some work with the topology. And we also prove, for example, that if you take the one-dimensional affine group over this ring FPT, that's the additive group extended by the group of units. This group is bi-interpretable with this ring, and it follows that, and this ring is finitely axiomatizable among profinite rings, therefore this group is finitely axiomatizable among profinite groups. So this was interesting to me because this group is not usually finitely generated as a profinite group. So it's very far from having finite rank. It's not even finitely generated. Okay, finally, let me just give you a couple of problems because this is Korovka notebook. Okay, can you characterize the soluble pro-P groups of finite rank, which are finitely axiomatizable among profinite groups? We did the nilpotent case. So the soluble ones are polyprocyclic. And so the analog for abstract groups was proved by Lasserre. He proved that a virtually polycyclic group is finitely axiomatizable among finitely generated groups, if and only if every subgroup of finite index satisfies this necessary condition about its center not being too big. So it's possible that an analog for pro-P groups, procyclic, polyprocyclic pro-P groups, might be proved, but I can't do it, but hopefully somebody can. Finally, here's a whole class of problems. We know nothing about, for example, finitely presented pro-P groups in general, if they have infinite rank, in terms of their axiomatizability. For example, if a free pro-P group on two elements, if G is a free pro-P group on two elements, can it be finitely axiomatized among pro-P groups even, let alone among profinite groups? The answer is we don't know. It can certainly be axiomatized. No, I won't say that. Okay, we don't know. So that's a kind of open question, which I think would be quite interesting. Anyway, I'll stop there and thank you for listening.
Thank you, Dan, for a very interesting talk. Clap hands. But anyway, there is time for questions or discussion, and I see already a hand raised by Natalia Maslova. Is there a question, Natalia?
I'm here.
Yeah.
But
you have a question, raise the hand.
No. Sorry, it's misprint.
Okay, all right. Anyway, are there any questions? In particular, I have a question about possible analogous results or maybe theory for Lie algebras. You probably can pose similar questions about finite axiomatizability of Lie algebras in certain classes. Does it make sense?
Yes, absolutely. Yes. I don't know that anybody has actually written anything about this, but it certainly makes perfectly good sense. Yes, you can translate everything directly. I mean, the same question obviously makes sense.
Because you mentioned also that some of these type of questions are kind of easier for rings, and
well,
it could be possible that it's easier for Lie algebras, and then sometimes maybe using exponential map you could translate something from Lie algebras to, at least for p-adic analytic groups, one would expect a strong connection.
Yes. Yes. In the p-adic analytic situation, you might have a bit of difficulty with the language. I think something that might be worth considering is if you allow your language to have symbols for analytic functions or something.
Or maybe just p-adic powers.
Well, p-adic powers you certainly would need, yes. So I don't know, I think this is an area which could be interesting to explore, certainly, though I haven't explored it.
Thank you.
So yes, it would be interesting actually. Would the Lie algebras be more like rings or more like groups in terms of inaccessibility to first order logic? Because associative rings, you can say it's very easy to write down a lot of properties of associative rings in the first order language of ring theory. So maybe Lie algebras are a bit harder and more like groups, or maybe not, I don't know. I think that would be interesting to explore, certainly.
Okay, thank you. Other questions? Maybe some comments. Wolfgang, you raised the hand.
Hi. I have a question related to slide number 31. I hope it's not a bad question. It's about the center of the centralizer of a non-trivial element of a root subgroup.
Yes.
I was just wondering what happens if you look at, for example, projective special unitary groups. I think in this case, I think we passed it. I think in this case, the root there will not be a root subgroup that's abelian in this sense.
Well, the unitary group is not split, you see, that's the point.
Right, okay.
Yeah,
okay.
yeah.
Okay,
yes. On the other hand, according to my co-author Katrin, essentially the same arguments should work for any isotropic reductive group. So, but I'm not sure what they would result in. I mean, we haven't followed this up.
Thank you.
Yeah. Okay.
Okay, thank you. Other questions, maybe?
I have one other question, a remark. It's Alexei. Hi, Dan.
Hi.
Actually, the slide that you're showing, you can do a little, it's not only the center of the centralizer, but you can pick some root elements and consider the centralizer of several elements. So you don't need the center. In this case, you define by equations the root sub, this u alpha, and you can interpret, you can solve their finite problems as well.
You mean you don't need the center of the whole centralizer, but you mean
right?
The centralizer finitely. Yes, in fact, that is exactly what the proof does.
Yeah.
For the proof, we find finitely many witness elements.
Precisely, and then you have interpretability by equations, which also affects. You can not only first order formulas, but you can reduce equations
absolutely
from
yes,
groups
yes.
into equations into rings, and
yeah,
decide the finite problems.
Yeah, this is absolutely true. Yes, thank you.
Okay, thank you. More questions, maybe?
May I ask something? I apologize in advance. I made a mistake and I was late to the talk, so maybe it was mentioned, but I'm wondering if the method can work also for congruent subgroups.
Ah, is that Alex? Hi, Alex.
Hi. Yeah, I'm
Yeah.
sorry.
Oh, I can't see you.
I miscalculated the time and I was late, so.
Oh, at least you weren't giving the talk this time. Congruent subgroup. Well, in the first part of the work, we actually do it for the congruent subgroup first, not the bi-interpretability, but the explicit axiomatizability we do for the congruent subgroup first. In this case, I think the answer is probably yes, but I'm not sure if it makes it better anyway. I think you can deduce it for a congruent subgroup because the congruent subgroup will be defined by some extra condition. Does that make sense?
Well, to be honest, I have in mind something specific that I want to understand the difference somehow between the theory of a group and a finite index subgroup. So I know that for the important groups, sometimes you can find finite index subgroup, which I think have the same first order theory as the group, cannot distinguish between them. In the more general case, well, we know, of course, in a free group by Sela that they have the same theory, and somehow I wonder where is the difference somehow. Like,
right?
Is there some principle that can, and because your work is very much connected with the structure of the ring, so I'm really asking about congruent subgroups and not about general finite index subgroups. So assume you have the congruent subgroup property, or
well, I think you could. I mean, you can obviously define a congruent subgroup once in terms of the ring, can't you? And an ideal.
Probably yes. I mean, the principle, I'm sure you can, and probably you can also define every congruent subgroup. So it makes sense that you can define them in terms of the ring.
But then what can you formulate a precise question?
I'm not sure, but but even this, I mean, like you prove that the theory of the full Chevalley group is bi-interpretable with the ring. Take a finite index subgroup, and then you deduce for me that I don't know, that its theory is given by one sentence. Can you say it for a subgroup of finite index in SL3Z?
That the subgroup of finite index in SL3Z, its theory is defined by a single sentence.
For example.
For example, I
mean, to be honest,
I'm sure the answer is yes, but I agree it doesn't immediately follow. I think it needs some thought.
Yeah, I think some of the work of Avni and Avni implies that, but
yes,
in this spatial case, but I'm not sure if there is a general principle which would say that.
I mean, Avni and Mary have this very interesting thing, but for groups over Z, where they uniformly define all the congruent subgroups, but that takes you in a slightly different direction. But yes, well, certainly the congruent subgroup isn't isomorphic to the group. You see, it follows from this.
Of course not. It's not isomorphic. I mean, the other way around. I mean, it's
you can see anyway.
Rigidity, Margulis rigidity, for example, tell you that they're never isomorphic. But to my surprise, I discovered recently that even in SL3Z, that subgroups of finite index there, which are not isomorphic, may have the same profinite completion. The profinite completion are isomorphic.
Right.
So it's kind of, I didn't know that before. And so which kind of interesting, because sometimes it goes together, sometimes it does not, like whether the theory of the profinite completion and the first order theory are going together. I mean, I think there are examples maybe in both directions. It's not completely clear to me, but
yeah,
they don't.
It's like Francis Auger did a lot of stuff about that, didn't he? Many years ago.
Right. So
for something, certainly for, I think for nilpotent groups, finitely generated nilpotent groups.
so this is equivalent, like the first order theory are equivalent if and only if
Something like that.
Yeah, I have a vague
And
memory also like that. So it's not
but
true for
my memory is also
arithmetic
vague.
groups. So this is not true for arithmetic groups.
Yeah, no, I believe that. Yeah. Yes, good. Some questions there.
Questions maybe or comments? Okay, if not, then we can thank our speaker again. And
thank you.
I'm not sure if there are any announcements by the organizers in Novosibirsk. But anyway, the future seminars will be announced as usual, and we welcome everybody to join again for further seminars in this series. Thank you, Dan, again.
Thank you for inviting me.
Yeah.
Good to see you all.